In this video, I want to dig a little bit more into the topic of the genetics of obesity. Now, more evidence for an important role of genetics in obesity comes from humans and animals that have a genetic defect in the regulation of food intake. Now, previously, we talked about the hormone leptin and its role in regulation of food intake. Now, the reduction in leptin levels in the blood after fasting or weight loss leads to strong hunger sensations. Obviously, if we wouldn't feel hungry after we didn't eat for a while, we would run a huge risk of underfeeding ourselves and becoming malnourished. Now, evolutionarily, such a scenario would not be very conducive to the survival of our species. The reduction in leptin upon weight loss and fasting should therefore be considered as a very important basal physiological response. Now, some humans and animals, however, have a defect in their leptin gene and cannot produce any leptin. And the consequences are pretty obvious and include a voracious appetite and severe obesity. Now, the image shows a normal mouse and a leptin-deficient mouse. Now, the leptin-deficient mouse is very fat because it eats all the time. And the lack of leptin prevents it from becoming satiated. Now, leptin-deficient humans have the same problem. Now, imagine how hungry you would be if you skipped several meals. Leptin-deficient individuals experience this type of hunger all the time, and as a result become severely obese. Now, a deficiency in leptin production are very rare, although they do exist. Now, in a small number of highly obese individuals, the state of obesity can be linked to a defect in a specific gene, and these so-called monogenic forms of obesity are very rare. And many research groups have been searching for new genes that influence food intake and obesity. And their efforts are partly driven by the hope that it may lead to development of new drugs that reduce hunger and trigger weight loss. Now, they have focused their attention on genetic defects, or better, genetic variants that are relatively common in the population and that have much more subtle effects on body weight. Now, so far, about 75 common genetic variants have been linked to obesity. And together, these common variants explain a mere 2 to 4% of the variability in BMI that is attributable to genetics. And researchers have not yet been able to explain the remaining 95%. And some people actually think that this so-called missing heritability may be accounted for by rarer variants that haven't yet been identified. And other people argue that there is a strong interaction between genes and the environment, which most studies have ignored. Now, it's also thought that the missing heritability of obesity is related to what we call epigenetics, which describes chemical tags that can change the activity of genes without altering their genetic code. Now, as an illustration, I want to show you the result of an experiment in which several groups of individuals were allowed to eat as much as possible in one setting from a table stacked with 4,300 calories worth of food. So imagine you're given access to a table that's stacked full of food, and you're told to eat as much as you can. Now, what was very interesting is that leptin-deficient subjects ate the equivalent of 8 Big Macs, whereas control subjects could not even finish the equivalent of 2 Big Macs. Now, treatment of the leptin-deficient subjects with leptin drastically reduced their appetite. And the experiment also included patients with an inactive or partially active MC4R. It's a receptor that's present in our brain that's responsible for some of the effects of leptin and is involved in regulation of food intake. And defects in this MC4R are fairly common, and they may account for up to 5% of the severe obesity cases, according to some estimates. Now, what about fat distribution? Now, we all recognize that some people tend to store their fat on their thighs and buttocks, whereas other people have proportionally more fat stored in their arms and upper body. Now, gender is a very important factor. It plays a very important role in determining where the fat is stored. In addition, there is solid evidence that body fat distribution is controlled by genetic factors. And similar to what is observed for total body fat, there are a number of rare genetic variants that dramatically alter fat distribution, and they lead to a condition that we call lipodystrophy. Now, affected individuals often carry very little body fat on their lower extremities, whereas the amount of fat stored on the trunk is normal or elevated. Now, scientists are trying to figure out and find novel fat distribution genes in an effort to find ways to influence fat distribution. Now, when we look at the relation between genetics and obesity and consider the role of environment, what we can say is that scientists that study the environmental influence of obesity often have little appreciation for the role of genetics. They and many other people argue that our genes could not have contributed to the current obesity epidemic because obesity rates only went up in the second half of the previous century. And during that limited time span, our genes definitely didn't change. Now, geneticists feverishly keep on searching for obesity genes, hoping to identify novel inlets to tackle the obesity problem. Now, while genetics has failed to deliver that, their work has provided very important insights into why obesity develops, and particularly why some people are more prone to overeat and become obese. Now, during the era when food was scarce and people did not have heavy labor to earn a living, very few people were obese. Some people did have a genetic propensity to become obese, but that didn't happen because the environment didn't allow it. Now, evolutionarily, obesity-prone individuals may even have had an advantage by being better able to survive periods of famine or underfeeding. Now, nowadays, we're living in a different environment. We're living in the obesogenic area, where numerous factors conspire to stimulate overeating. Now, in the current food climate, people with unfavorable genetics don't stand a chance, as their natural tendencies, coupled with the overabundance of highly palatable, energy-rich foods, lead them to overeat. Now, people with favorable genetics should consider themselves lucky. However, not with the iron discipline that they mistakenly accredit to themselves, but with the fact that they're naturally less drawn to food and simply have a smaller appetite. Now, it's widely accepted that changes in our environmental factors explain the overall increase in obesity prevalence. But the inter-individual difference in BMI are for a large part determined by genetics. Thus, a proper way to put it is that the presence of obesity among a large fraction of the population can be attributed to an interaction between genetics and the environment. Now, a recent review article published in the New England Journal of Medicine by Dr. David Allison and colleagues concluded that although genetics plays a large role in obesity, heritability is not destiny, meaning that the role of genetics can be overcome with sufficient environmental influence, at least for most obese individuals.